Section 9.6 is on absolute convergence and the ratio test. We'll start with absolute convergence. A series is absolutely convergent when the absolute value of the series is convergent. To be conditionally convergent means that your series is originally convergent, but the absolute value of your series is divergent. Now, I've made mention of absolute value, so this alludes to our alternating series. So my first example is an alternating series. So what I'm going to do first is check this series by using the alternating series test. For the first condition of the alternating series test, I am going to check if the terms are decreasing. So let's compare our nth term with the next term. The next term would be 1 over square root of n plus 1. Now the denominator of our nth term is smaller than the next term. So that means our fraction is bigger. And that indicates that the series is decreasing. Check the second condition of the alternating series test. This is the one where we're checking to see if the terms decrease towards 0. So let's take a limit as n goes to infinity of 1 over root n. The limit is 0. Therefore, the series is convergent by the alternating series test. By the way, you can abbreviate this as AST to save time. Now that we've concluded our alternating series is convergent, let's consider whether the series is absolutely convergent. So that's what I'm going to do next. Consider absolute convergence. And if you check back up at the top, that means I'm going to look at the absolute value of the series. I'm going to look at the series absolute value of negative 1 to the n times 1 over root n, which means I want to look at the series of just 1 over root n. This is a p series with p equal to 1/2. Since p is less than or equal to 1, the series 1 over root n is divergent. Therefore, our alternating series is conditionally convergent. The term conditionally convergent means this. Our series is only convergent on the condition that it's alternating, because as you could tell, when we removed the alternating component of the series, it was no longer convergent. Now it was divergent. So that's what is meant by conditionally convergent. This series is convergent only if it is alternating. We will check number 15 to see if it is absolutely convergent. Starting with the alternating series test, let's see if the terms are decreasing. This particular nth term has an n in the numerator as well, so I am going to look at our nth term as a function, and that means I can take the derivative of it, and I'll have to set up quotient rule. I will simplify the numerator. Checking the denominator first, I can tell the denominator will always be positive. Whether the derivative is negative or positive depends on the numerator. As you can tell, in the numerator, I will get a negative answer as long as x is greater than 2. So I'm going to indicate that this derivative is negative for x greater than 2. So that's a little different than the original math problem, which indicated we were going to go from 1 to infinity. I warned about this earlier, where sometimes the series will satisfy some condition if you just change where you start your series a little bit. It's not a problem to start at 2, or greater than 2 in this case, than to start at 1. Look at the second condition of the alternating series test. I'm going to divide numerator and denominator by n squared. Now I can take the limit. The limit equals 0. That means our terms decrease toward 0. Now that we have convergence, let's check for absolute convergence. We are going to look at the absolute value of our series. We're going to look at the series of n over n squared plus 4, not the alternating series. I'm noticing the dominant term in the denominator is the n squared. I'm going to compare with n over n squared, which is the same as 1 over n. If I compare with n over n squared, my denominator is greater than the denominator of the comparison series. So if my denominator is greater, that means my fraction is smaller. That means n over n squared plus 4 is smaller than 1 over n. But we know the series 1 over n is the harmonic, which is divergent. If our terms are less than the terms of a divergent series, we cannot draw a conclusion. If the comparison series is divergent, we would want our series to be greater than that and then show that our series is divergent. But they're not. Since our terms are smaller than the comparison series, we kind of need that comparison series to be convergent because the comparison test is not working. So we're going to choose to use the limit comparison test. I'm going to divide both top and bottom by n squared. When I take the limit, I'll get 1 over 1 plus 0, which is 1. That happens to be positive. We just confirmed that our series diverges by the limit comparison test. And remember, we were trying to prove absolute convergence for the alternating series, but we cannot because the absolute value of that series ended up being divergent. Therefore, the original alternating series is conditionally convergent. I have one for you to try. Please pause the video and try this one. Check for absolute convergence and then turn the video back on to see if we got the same answer. For condition 1, I will take our nth term and compare it to the next term. I'm going to replace n with n plus 1. Our denominator is smaller than the comparison series denominator. Since our denominator is smaller, that makes our fraction larger. And that means that our terms are decreasing because the next term is smaller. Look at the series without the alternating component. So just look at 1 over n squared. This is a p series with p equals 2, which is greater than 1. Our series converges. This means that our original alternating series is absolutely convergent.